So as already mentioned, I work at Actyx, and at Actyx we do software for factories. And well, this is one of our products. It's called EOS, and it's a real-time production monitoring software. So you can see various production stages, what's happening to them, and it obviously has some sort of data acquisition side of it, so you just gather the data about the production process. And this is factory. This is where our software thrives. The photo is quite old, it's from the 50s. It actually could be anywhere, because it's a photo that passed as a photo of a German factory floor, but actually was made in Poland. And if you would walk into a factory now, you would see something very similar. So it's not much different. Of course, there are futuristic factories with robots and everything, but most of the factories actually look like that. And now on to serverless. What's serverless and how do I understand it? So serverless is actually two words. One of them is server and the other is less. And if you think about other words like jobless, for instance, what happened to computer programmers after the dot-com crash? They just went out of work. So someone who is jobless doesn't have a job, although they would like to have one. So something less is without something. And then we can decode this serverless, which means that is something without a server, obviously. Well, it doesn't mean it doesn't run on servers, on hardware. It just says that it's rather client-only without a designated central server feature. So rather peer-to-peer technology. And there are many cool peer-to-peer technologies already discussed. I would like to draw your attention to two of them. One of them is Bitcoin. You've probably heard about it. And the other is, I don't know if you heard about it, Internet Protocol, which has been designed by the Defense Agency for Research Projects, or how it's called. It was designed for battlefield, so to survive the harsh conditions of the battlefield. It's really good peer-to-peer technology. And now why? This is because that's a factory on fire. And okay, it doesn't mean that most factories are ending up as that, but it just means that factories are very rough places. So like internet is being disconnected, power is being disconnected, computers got destroyed, and all the bad stuff is happening out there. So the main tenets for the software to actually thrive at the factory is one of them, ability to operate despite failure, maybe in a degraded mode, and the other is to be able to operate in a hostile environment, exactly like the IP protocol. And assume I'm working at a company that does software for factories, and I'm commissioned to write an application that would help to gather all the raw materials necessary to finish a production job. It even has a name. It's called order picking, and it's quite a common application of software for instance, at Amazon and every warehouse. So logistics software. Okay, so this is raw material information. I have lots of that. It says I have an article that's glue, and I need 50 of it. It has an ID, and I haven't picked it up, and now I have picked it up. So now I have my glue. It's just it. And I'm working around, changing this information. Well, this is raw materials for an order. This is a tree. So it's kind of a tree structures. And I have order ABC1 to 3, and I need to pick GX1 to 3, QZ1 to 5, and so on. So you might think that storing JSON in a tree, perfect match for a MongoDB, but not exactly, because we already said that this is the environment where we thrive. And suppose your terminal for picking is connected via Wi-Fi, and as you can obviously imagine, there are many places where Wi-Fi has poor reach or something is flaky, and so on. If you create a web page connected to a MongoDB network, you'll end up most of your life troubleshooting connecting issues to the MongoDB. So we can do better. And we can do better by just distributing the data. So every worker picking the order just carries their own data with themselves. And that's it. Okay. So what technology to use to do that, actually? So how how to come up with something suitable? Well, let's take something most hip that there is out there. And that would be something that combines BitTorrent, Bitcoin, blockchain, Gits, and distributed file systems and whatnot. And this is actually called IPFS, which is a peer-to-peer distributed file system. It uses BitTorrent-like protocol to distribute the information in the swarm. It looks like Git to you, and it uses block storage, and it uses all the cool stuff from the blockchain protocol, and is actually part of the some sort of file chain project. All right, so how to per-use it to my needs? I will not use the raw IPFS. I will use something that's called IPLD, which is some sort of DAG, directed acyclic graph, running on IPFS. To give you an example, how to use it, the API of the IPFS, I just need to install a daemon on each of the computers that need to be running in a swarm. I can run them in the private swarm, so this can be running in my factory computers. And, well, if I want to store an object, I just pass it to IPFS DAG put, and then you receive a hash of this object. And the coolest thing about it is actually the hash never changes, because if you put the same contents again, you'll get the same hash back. It's content addressable storage. And if you want to get it, you just name the hash and you get your object back. You might just have noticed that this is a bit of formatting down there. It just formats JSON to canonical representation. But otherwise, it's just fine. So far, so good. I can store it. I can retrieve it. I can even code it in Scala. So this is IPFS DAG put. And then I just pipe it to CMD. What about returning value? I just return some if it's OK, and none if it's not. You can bring whatever construction you want. You can bring either validation, null, whatever, whichever library you like. I think John Petty a couple of years ago just shown a library where you just plug the mod functor that you would like to be returned, and that's it. And this is getting. From the DAG, you just say IPFS DAG get path, and whatever the contents it's return, you just return wrapped in a sum. Okay, so, and interestingly enough, IPLD makes IPFS DAG get also work with this construction. So if I have some root hash that I've already calculated for this construct, I can say /order /bcd /materials /gx something, and that will get back exactly that. Okay, so how it works? Well, after I've put the thing in, I got a hash back, and then I just construct a special JSON. That's what IPLD says. And this JSON needs to have a name. There's going to be a part of the path, and then another JSON inside with a slash. That's a special. It's like a link in HTTP. And then you just put this hash. And that's it. So basically, you can model this as a table of hash to JSON. And the JSON, well, will either be just a JSON, plain JSON, or something containing a slash. And if it has a slash, then it has a special meaning. So I can say IPFS DAG get this hash, and then I just get the object, or I can /gx123, and then I'll get the other JSON back. So far, so good. I can even model it with Scala, so to get better understanding. And to actually show you how I could test it, I just have a test implementation. So this is my content addressable storage. It's just a map from string, which is actually a hash, to any. And when I'm putting it, I just calculate the hash and as a key. Then I do this cool trick that Scala has. Actually, Scala can do JSON, half of JSON. So if you put a string, then it'll turn it back to its representation of maps and lists. It cannot do the other way around. I don't know, they were shy. They wanted to the industry of JSON libraries thrive. So like in my past project, I had like 5 JSON libraries, and I ended up writing implicits, converting JSON from JSON to JSON via string. So there would be an implicit that would take any JSON representation, just turn it to a string, and pass it to another JSON representation. And then I just, put it into the content addressable storage. And then return some of it, and if there's a problem, I just return none. Okay, so getting the contents is a bit more involved. I encoded this as a function, a path tracker, and the path tracker actually needs to deal with 2 cases. One of them is label to a string, and the other is actually that our map, which there's label to a map. So it works like that. It just splits the path into elements, and then I go through all these elements, and then, first of all, this is the cases I need to consider. So first of them, if it's in the map, I'm going to probably get a string of it. There's some other compact representation I haven't mentioned that's also in IPLD standard that I could have it encoded in one map, but I just don't use it because it would like put everything into one object, which I do not want. I want that to be composable. And then I need to consider this case. And in that case, I just need to go further into that map. So I just deconstruct it. I'm getting the slash. And then after I got a slash, and if it's successful, then I just would go to the element that's under that slash. Believe me, it works. Then I need to return some to JSON, and this is actually what Scala doesn't have. And if someone could be so nice and just copy and paste from Stack Overflow into the Scala standard library, then we would have JSON representation working both ways, because this toJSON function just makes go from map to a JSON. So this is cool. This works, even in tests. But what about the ability to actually create such paths? Okay, free monad is going to help me. If you don't know what a free monad is, well, you should read a good tutorial. There's one of the good tutorials about free monads, and there's a couple of more good tutorials about free monads. So the free monad, starts with that. This is just a boilerplate, so functional programming also has a lot of boilerplate. These are just case classes that would be representing our put and get functions. And there's an interpreter. You need an interpreter because free monad is just a code that runs on an interpreter. And I've just pasted the real interpreter, which just runs a put and get functions. Okay. Handling errors logic is up to you. So you should think about something. It's too simplistic because 30 minutes is too short. So that's a more boilerplate. We need the lifting function, okay, because it's like the monadic programmer is like lifting, and here is actually that. And even a nice programmer just put a to do there to move later to either, because it's like you should be on the lookout for to do in the code if you're looking at the code, because that's a fracture line. Most errors are in to dos and fix me's. And that's my program. So I can run it. I put to JSON map A to A, and then I get SHA string, and the result of that would be just a JSON AAA and then AAA. There's a bug on this slide. You might have caught it. If you didn't, I will just show you in a minute. And the test interpreter is just the same thing. It just plugs our test code that we already discussed. So I can actually test it. And testing that, I'm just doing what I've been showing. So I'm putting AAA to AAA. There I'm just putting this thing that maps BBB to this slash and the SHA string of this toJSON map. And then I just can get it. This root hash would be just calculated by hand here. And I'm just getting this BBB. And it runs on test interpreter, really cool. But it will not work on real interpreter, because actually I'm using the test SHA implementation. So I need to actually take this returned hash, and this will work both on the real and a fake interpreter. So far, so good. What about the nested structure? So for every case, I would need to write a code like that, and this is going to be probably quite complex. And if you are into functional programming, you've probably heard about something that's called lenses. So if you're up to that sort of manual work, you would probably turn to a lens. But the problem is, we are now running lifted. So we are not running on a computer, we are running in an abstracted monad that's running on a computer. So our program is actually not an operation on a structure, it's just a program that after executing it will just operate on a structure. So how to do about that? You can create a program in your monad. So this is what free monads are really good, not only the ability to plug test library and production library, also the ability to write programs in your monadic language. So if I want to have an application, I just can put it in the language of the monad itself. I've called it Fresnel Lens. Fresnel Lens. It takes a it takes a hash, here fake hash because I don't know. I'm just starting with an empty hash. I don't know the hash, so I can make up any. And then it takes a path and the object that you want to put there. And then it just returns the hash of the whole structure, and you can get it. So you can say n get root get /b/c and /d, and you'll get your object back. Why Fresnel Lens? Because Fresnel Lens is can be made like from those rings. So it's like a bit of like telescope. You have many lenses and you look through this telescope, and this is exactly the way how we would like to compose our operation. So we just, what we need basically here, we just need to run a sequence of operations. Take an object, wrap it in a JSON containing slash and reference to hash of it, and return a hash. And then take this hash, wrap it up in a JSON containing slash, and return the hash of it. And then, and so on and so on. Of course, every time adding an element of the path. So this is basically our program. And I will write it in a monadic language. So this is a simple composed update function, which does exactly that. It uses a get and a put and a monadic constructor, which is called pure or point, whatever you want. It just composes get and set. By the way, that's an example from the excellent CATS library documentation. I just copy and paste it and adapt it to my use case. So it's very easy to follow it in the documentation. It's actually, I didn't need to actually consult any forums or something. Okay, so Fresnel Lens looks like that. It has a single Fresnel Ring that would actually do this operation of taking out a hash, combining it with a slash and a path element, and then put it back. And what I would need to do, I would just need to run a fold with a Fresnel Ring, folding this with the path structure. And the path structure should be like all generated paths, so like ABCD. For a path of ABCD, that would be ABCD, ABC, AB, and A in the end. How do I do it? How do I figure out the upper part of it? I just use Scala Fiddle, which is cool. And I tweak in the Scala Fiddle until I figure out what code to put there. That's the most basic solution I would use. And that's the same example. So here we have an example of a path. The split path would be a path split to elements. Subpaths would be exactly that list I was talking about. So ABCD, ABC, AB, and A. And the paths itself would be the same with the existing hash attached. So I would just be traversing this structure. So this would go exactly here. So I'll be folding along those paths and using a single Fresnel ring, which would then just perform this operation. So the operation itself would be exactly that. We have a path, a label, which is just the current element that we want to fuse with the slash, and label path, which is just a remainder of the path. So I take an element, I combine it into that structure. I don't know if you program in Scala. If you program in Scala, you can use this cool string thingy to get your JSON. But actually, if you do string approximation and then you put a escaped quote into that, it will fail and it's a bug, and it's been registered for a couple of years, and actually no one can fix it. Enough complaining, so I'm just putting that element, I'm just moving it to JSON, then I'm getting the label path, and then I'm flat mapping it, so I'm just combining two elements, because that's the, that will run on a fold, in just a combination that will run in a fold, so I need to use a combination operation, which is going to be a flat map, and I'm just putting it to there, and returning, so actually, my program will be a very long flat map combinator. That will be run on a monad. By the way, there's a command there. Fix me, checks content and merge. Be on the watch out for comments, because the problem is that this code will not work exactly as advertised if I have a situation where two paths are going to be diverged, because I just put a JSON with a single path. So if I had already a JSON there, then I would just replace it. So I need to actually combine those two JSONs, but it's a very simple operation. I just pass the JSON, turn it into a map, and then just add that element to a map. I think this beats every JSON library out there. It's very simple, and I actually prefer to use JSON that way. So like turn it to a structure, and then process structure recursively, maybe just use the basic operations, and then just turn it to a string, which actually JSON is. This is more closer to a JavaScript way of working with JSON. If you have ever worked with JavaScript or TypeScript or any other kind of script, you would see that working with JSON is very natural out there and doesn't need actually any library. Okay, so now we only need to map the stream of hashes to the order ID, because the hashes will be changing. When I'm picking the elements, the returned top-level hashes will be changing. By the way, this is cool, because it's like event streaming. I'm creating a history of hashes, and I can refer to every other hash and get back the structure exactly as it was back at the moment where I created this hash. So this is good for evidence purposes at the same time. So how do I map the stream of hashes to the order ID in the way that can survive this factory? I just use Akka. Sorry, John. I'll be using actually CRDTs, because CRDTs work in a cluster, so my mobile terminals can be a part of Akka cluster, and this is a simplified CRDT that actually assumes one very important business thing, that every picker is picking just one order, and they don't exchange those orders. But I could model that situation where two people are on the same order with CRDTs, but that would be more complex CRDTs, like the one I discussed a year ago. So last write wins map is just what it says, so the newest write will just do a replacement. And there's a map from order ID going to the current hash. And if you look at how Akka cluster works, so this is a global structure, and let's say I do a replacement here, then this replacement will get magically propagated to here. And cool thing about Akka cluster is that if I do a replacement on the mobile terminal, I lose a connectivity, and I get back to the cluster, then my updates were going to be propagated to the cluster. The second cool thing is that everyone in the cluster will know about my hashes, and they also have IPFS, so if they want to know what I'm doing at the moment, for instance, for dashboard display, they just get the hash, go to the IPFS, and get the whole structure, or just the parts they are interested in. And the third cool thing is I'm just adding a new terminal to the solution, and it will just get the whole structure replicated. And That's maybe not the exact technology that we use at Actyx, but it's close enough to some of the problems we are actually solving in our work, and that comes most closest to actually, my daughter's question, Daddy, what do you do at work? Well, I've tried answering her. She's 9, and her idea is now that I play the computer all the day and then I do party. I hope your impression is as good as mine. Thank you very much. In case of any questions, the office hours are soon. Thank you.